What we'll do is we'll get started with Laplace transform, and then when we get a little deeper into the material, I'll talk about the whole control system process.
Laplace.
Please start talking.
Laplace is for A class. What did you say?
So Laplace transform the definition of Laplace transform is if you have a function f of t, the Laplace transform L of f of t is defined as it's denoted by f of s, okay, and it's defined by integration of 0 to infinity f of t e to the power of minus at or minus st dt. Okay. And similarly, the inverse Laplace, so if you have f of s is defined as 1 over 2 pi j integration of sigma minus j infinity through sigma plus j infinity f of s e to the power of st ds. And this will result in f of t u of t. Okay. So here you have to understand, so pay attention here a little bit, okay? F of t, what is f of t?
Function of t.
Function of time, okay? It's a function of time.
You said that's j infinity?
Yeah. J infinity plus j infinity, okay? It is essentially, this is a complex number.
That's sigma.
That is sigma. Sigma minus j infinity through sigma plus j infinity. So f of t is a function of time. Okay? And we introduce something called this s, small s, is the Laplace variable or the frequency variable. So what you're trying to do is you have a function of time, you apply Laplace to it, and that transitions to function of frequency, okay, or Laplace variable. All right. Now keep in mind this notation is very important. Whenever we are going to use function of time, we are going to use small letters. Okay. When we use function of frequency or Laplace variable, we are going to use capital letters. Okay. And similarly, if you have f of s, okay, you apply inverse Laplace, you're going to get f of t. For assignments, exams, you will be given, you can use the Laplace transform
Table.
and inverse Laplace transform tables. Okay. Why do we need Laplace transform? So what you've learned until now is, pay attention here. Just think about this example, a physical system, right? So you have a mass of m, okay, which is attached to a damper, right? And then there is a spring of constant k, this is of constant c, and you have this is the displacement x of t, and there is a force being applied here, which is f of t. Alright, so what you've learned until now is, if you apply Newton's second law to this, you know how to model this dynamic system, right? What you do is, you say f of t is equal to mx have d square over dt square of x of t plus c into d over dt of x of t plus kx. Okay, so what you're saying is this, if you apply a force here like this, that force will cause displacement. These are other components of forces. This is essentially applying Newton's laws. So what you're trying to understand here is, what is the input? Input is f of t, right? What is the output? X of t. Got it? X of t, or if I write this again, if I write it like this, f of t is equal to, this can also be written as m x double dot of t, right, plus c x dot of t plus k x of t. So output can be x of t, x dot of t, x double dot of t. Okay, this is displacement, velocity, acceleration. All right. Now, if you apply Laplace transform to this, so Laplace of this entire thing will get you f of s equal to m s square x of s plus c s x of s plus k x of s. So compare, this is what kind of equation is this? What kind of mathematics is this? This is a differential equation, right?
Yes.
You can say this is a ordinary differential equation, right? What kind of equation is this? This is a
Partial.
polynomial, right?
So how are you getting M for acceleration, C for velocity, K for like?
Right. So when you apply a force, okay, there is acceleration. This moves, right? Mass moves. Okay. So mass into acceleration. That is clear. So when you apply a force like this, the spring force will be in the opposite direction. Okay. And the spring force is proportional to the spring constant into displacement. Okay. So if you can see, if I write this even before this, it can be written like this: F of P is the applied force, okay, minus K x of T. If I apply a force, the spring will try to pull it in the other direction. That force is proportional to the displacement multiplied by the spring constant. Minus this damper, what it will do is, depending on the velocity, it will apply a force in the other direction. The damper, you know what a damper is, right? So all these doors have dampers.
Oh, the thing that slows it down.
Right. So the force is proportional to the velocity with which you apply this force. Okay. So this is the. So if you push like that, damper will try to push it in the other direction. It will proportional to the velocity and damping constant. Okay, or a coefficient, damping coefficient. And this is equal to what? Simply mass times acceleration, right? And you're just seeing that here, but things are moved in the other direction. Okay. So this is the ODE, or the ordinary differential equation. This is polynomial in S. Okay. Now, let's look at a very simple utility of Laplace transform. Okay. What is a simple utility of Laplace transform? Think about this. Or let's do this. Let's do an example of Laplace transform. Okay. So if you have f of t, or let's quickly do partial fraction expansion and then look at utility of Laplace transform. Okay. We'll discuss this with an example. So if you have f of s equal to 2 over s plus 1, s plus 2, okay, and you want to write this as a over s plus 1 plus b over s plus 2. How do you do this? That's where partial fraction expansion comes in. So the easy way to do it is you equate this, okay, and then you find coefficients for A and B, right? So here this will be what? 2 over s plus 1 s plus 2 equal to A into s plus 2 plus B into
S plus 1.
s plus 1 divided by,
S plus 1 times S plus 2.
okay. So what you're going to do is this cancels. Alright? So now you can say 2 is equal to A plus B S, right? Plus
B plus
2A plus B. You with me?
Yes, sir.
So look at this. This implies A plus B is equal to 0. Alright? And 2A plus B is equal to what?
1/2. Or
Does that make sense? Can I write this as
yes.
this is a polynomial, right? What is 2A plus B? That's a constant term. You got it? The constant term here is 2. What is the coefficient of S? A plus B. What is the coefficient of S here?
Oh, 0.
0. So you equate coefficients. Right? You can, textbook gives you a different approach, but you can use this approach to figure out coefficients of A and B. So now, what you're going to get here is, you do minus, minus, minus. You're going to get minus A is equal to minus 2, right? Which implies A is equal to 2. So B will be equal to
-2.
negative. Okay, now you can write f of s is equal to 2 over s plus 1, right? Plus, sorry, minus 2 over s plus 2. So these two are the same, okay? This is just, if you add this, you're just going to get this. So if you add it, you're going to get 2 into s plus 2, right? It is 2s plus 4 minus 2 into s plus 1. That is 2s minus 2. So 2s cancels. You're going to get 4 minus 2, which is 2.
You said if you add f of s to...
No, these two on the right hand side, if you
Okay.
add, you're going to get this.
Okay.
Okay. So how do you get this or this from this? You use partial fraction expansion. You got it? Now, keep in mind, there are for partial fraction expansion, there are 3 cases. Case 1, roots of the denominator of f of s are real and distinct. Okay. Case 2, an example here is f of s is equal to 2 over s square plus 3s plus 2. Okay. What are the roots of the denominator of f of s here? 2 and 1. Minus 2 and 1, right? So minus 2 and 1 are real and distinct. You got it?
Wouldn't it be?
In this case,
Wouldn't they both be positive? Wouldn't they both be positive?
negative. So the roots are, we equate this to 0, right? They are negative.
But, well, if it was negative, then it'd be minus 3. Shouldn't it be s plus 1 times s plus
It will
1?
be this, right?
Yeah, but why? Yeah, that's what I'm saying. Like, but I'm just curious why.
And then you said it equal to 0.
Yeah, you
okay,
equate them to 0. Okay, and then what are the value of s's that makes them 0? Those are the roots.
Gotcha.
Okay.
Okay, now I see what you're saying.
Alright. So here, if this is the case, your partial fraction expansion looks like this. A over s plus 1 plus b over
S plus
s
2.
plus 2. You got it? So this is how it looks. If the roots are real and distinct, the partial fraction expansion looks like that. Case 2, roots of the denominator of f of s are real and repeated. Okay. I'll give you an example here. You have f of s equal to 2 over s plus 1 s plus 2 square. Okay. So how many roots are there here? How many roots are in the denominator?
3.
3 roots, right? What are the 3 roots?
S equal -1 and -2.
-2, -2.
Yeah.
You got it? So here the partial fraction expansion looks like this. A over s plus 1, okay, b over s plus 2, c over s plus 2
Squared.
Okay, so you need to figure out A, B, C. Finally, case 3, roots of the denominator of f of s are complex or imaginary, where you cannot split them like this. Okay? So here an example would be 3 over s into s square plus 2s plus 5. Okay. So here there is one of the roots is real, right? This s equal to 0 is real. Alright? This is, the roots of this are complex. So here the way you write it is, you write a over s plus bs plus c over s square plus 2s plus 5. because you cannot split it. Okay. So in all these roots, in all these cases, what is your end goal? What do you need to do?
Find
Roots are known.
find A, B, and C.
Find A, B, and C. Okay. So you're required to find. So you have something like this. You want to write it like this. So you need to find A and B. Okay. Here you need to find A and B. Here you need to find A, B, C. Here you need to find A, B, C. And the approach for doing that is very similar, like what we did here. Okay. Now let's look at what is the utility of Laplace transform combined with partial fraction expansion. Okay? This example is critical. I think you'll really understand the power of Laplace transform and the power of partial fraction expansion. So let's say you're given, and you'll get an example, get a problem like this in the exam. Okay, at least one problem like this will be given to you in the exam. Okay. So we call this Laplace transform solution of a differential equation. So we'll look at this example. Given d square y by dt square plus 12 plus 32. 12 dy by dt plus 32 y equal to 32 u of t. Okay. All these are functions of t. Y and u. And you're required to find the solution y of t. Typically, how do you do this? You solve for what is this? Do you recognize this as a differential equation? Everybody does that? Everybody recognize this? Yes?
I was asking Keith, like, I just couldn't see.
Okay.
Thank
Do
you.
you recognize that as a differential equation? Taurus?
Oh yeah. What's that? 32 yt plus or equal?
32 u of t, y of t equal to.
Oh.
Okay. So you can can you write it? You can write it as y double dot of t, right? Plus 12 y dot of t plus 32 y of t equal to 32 u of t. The same thing. These two. Now you are required to find the solution y of t. How do you do this? If you're using differential equations, you typically try to solve for y of t using separation of variables or a method similar to that. Okay? You remember doing that, right?
Yeah.
We'll look at the Laplace transform solution. So what we'll do is, step 1, so we'll call this A, take Laplace transform. So we'll use the short form LT, okay, for Laplace transform of A. So if you do that, you're going to get, you write it like this, okay. That is 12 y dot of t, 32 y of t is equal to Laplace of 32 u of t. You could use a definition of Laplace, or you could use a table. Okay. So here, what you're going to get is s square y of s plus 12s y of s plus 32 y of s equal to 32 1 over s. Okay. Work with me here a little bit. I'll talk about this u of t. This, huh? It's a unit step function, and it's typically u of t is typically 1. You got it? And the Laplace of 1 is 1 over s. Got it? So you're with me until this point? I've just taken the Laplace, and this is what you get. Okay? Now, your end goal is this. Okay? So now think about what are you going to get out of this. So if I take y of s common, I'm going to get s square plus 12s plus 32 equal to 32 divided by s. Okay? And y of s can be written as 32 divided by s into s square plus 12s plus 32. Alright? So again, keep in mind, what we really need is find y of t, which is equal to what? Laplace inverse of y of f. Okay? So what I need is Laplace inverse of y of s is what? Laplace inverse or inverse Laplace transform of 32 divided by s into s square plus 12s plus 32. Okay, so this on the left hand side, this will be equal to y of t. This will become y of t. Okay, but what is the challenge here? If you try to look up the Laplace inverse of this function in the table, you'll not find it. Okay, so what you need is you need to apply partial fraction expansion and simplify this into
S plus 4, S plus 8.
A over S plus, yeah, simple functions, okay? So what you're going to do is, now 32 over S into S square plus 12S plus 32 can be written as A over S plus, this is B over S plus 4 plus C over S plus 8. You with me? Okay, or I'll give you one more step in between. This is equal to what? 32 into S plus 4, S plus 8. Okay, so this can be written as A over S, B over S plus 4 plus C over S plus 8. So you see which this is the case which applies, right? This case applies. The roots are real and distinct. Okay. Now, if I equate these two, what am I going to get? 32 divided by S into S square plus 12S plus 32 is equal to what? A into S plus 4, S plus 8 plus B S into S plus 8, right? Plus C S into S plus 4 divided by this S into S square plus 12S plus 32. So this cancels, okay? Any questions? Aaron?
We're good. I was just asking about, but why wouldn't it be case 2? But is it
So
for
there
the
are
fact?
roots are not repeated, right?
That's what we just said. Yeah, I got you.
Right. So there are no repeated roots here. They are real and distinct.
I got you.
Okay. So you got to see this. If you add these two on either side, you need to equate coefficients. Okay. That is how we are approaching here. I won't erase this center part. Now if I equate coefficients, think what I'm going to get. I'm going to get A plus B, or let me solve it. Okay? I think it'll be better for you guys. So if I solve it, I'm going to get 32 on the left hand side equal to A into S square plus 12S plus 32, right? Plus B into S square plus 8S plus C into S square plus 4S. Okay? You're trying to compare coefficients here. I solved this. That's what I'm going to get. So here if you look at, this can be written as, see if you follow this, A plus B plus C S square, right? Plus 12A 8B plus 4C into S plus 32A. You good? Now compare left hand side and right hand side. What is A plus B plus C? 0. What is 12A plus 8B plus 4C? 0, right? There is no S coefficient here. What is 32A? Equal to 32, right? So this implies A is what? 1. We found one of them. Okay. So B plus C is what? Minus 1. And 8B plus 4C is equal to minus 12. Okay. So if I solve for this, I can write 4B, 4C, 4 minus 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 plus. I'm going to get minus 4B, this cancels, equal to 8. Okay, so which implies B is minus 2. And finally, if B is minus 2, you're going to get B plus C is minus 1, yes.
No, C should be positive.
C should be equal to, so B plus C is what? Minus 1, right? From this, which implies C is okay. So you found the coefficients of A, B, C. Now look at, I'm going to call this B. Rewrite B with okay. You're going to get Laplace inverse of y of s equal to Laplace inverse of 1 over s plus or minus 2 over s plus 4 plus 1 over s plus 8. And here you're going to see that this is simply y of t equal to Laplace inverse of 1 over s is what? Taurus?
So what?
Laplace inverse of 1 over s?
1 over s squared, ain't it? Oh no, 1 over s plus a or something. Right?
Laplace.
Oh, the inverse.
Yeah.
Oh yeah, 1.
Okay. Minus 2 e to the power of minus 4t plus e to the power of minus 8t. Okay. So look at what you did. All right. You had a differential equation and you solved for that differential equation. But you did not use any of the methods which you were taught in your differential equation class. What you used is you used Laplace transform and inverse Laplace transform, and in between you've had to use partial fraction expansion to figure out the solution y of t. Okay. Any questions so far?
Will you be giving us the table? Will you be giving us the table for the exam?
I'll give you the table, yes. You don't have to bring, I'll give you the table. So,
So what page is this on in the book?
This particular problem we just solved is in page 39. It's example 2.3. Okay. There will definitely be one problem like this in your first exam,
That's good stuff.
where you'll be required to find the solution y of t given a differential equation. Okay, you have to use your understanding of Laplace transform, partial fraction expansion, and inverse Laplace transform to solve that entire problem. There are three things which are happening. Okay.
It's good for us.
Yes.
Did you already explain why we have to use this? Like, how does this relate?
I'll talk about that a little bit later. Okay. I'll talk about why we need to use this. That will be the next section itself. So what we'll do is we'll stop here for today. We'll continue with for next class. What I want you guys to do is I'm going to give you, I think, we'll try to adopt this strategy where I'll tell you what we are going to cover in the next class. Okay, so that you can, if you want to be prepared, you'll read material relevant to it, or even you'll go and watch relevant videos from my previous lectures. Okay. The next class.
I mean, I've been having this since last semester. I might not use it, but I've been having
You got yours some homework too?
it. I was trying to be like my mom. That's what she used to love writing in agendas. I just can't get into it.
We'll talk about transfer functions. Okay. And modeling systems or dynamic systems. In frequency domain. Okay. We'll talk about this. We'll talk about in this we'll talk about basic spring mass damper systems. Which are very mechanical systems, okay? Mechanical aerospace systems. How do we model these? And that's when you'll learn the utility of this transfer. Now keep in mind, I have mentioned this in class last time. Your cell phones are banned in class. If I see you using cell phones, you will lose attendance for that class. Okay, unless it is meant for taking pictures, or I specifically ask you to do something. If you use cell phones, you will lose attendance for that class. Okay. Any questions so far? You going to be prepared for next class? Boris?
I'll try to be about that Sunday. I'm gonna have the pieces ready for you on that next class.
Okay.